Welcome to this session. In parallel transport, we are discussing about parallel transport. Last class, we have seen one theorem. Theorem was theorem 1. Let S be an n-surface in Rn plus 1. Let alpha from I to S be a parameterized curve, be a parameterized curve in S let T naught belongs to I and let V belongs to S of alpha of T, some T naught. Then there exists a unique vector field V tangent to S along alpha, which is parallel and has V of T naught equal to V. This we have proved in your previous class. Today we will see one of its corollary. Let S be a two surface in R3. Two surface in R3 and let alpha from I to S be a geodesic in S with alpha dot not equal to 0. Then a vector field X tangent to S along alpha is parallel along alpha if and only if both norm x and the angle between x and alpha dot are constant along alpha. So what does this corollary says? S is a two surface in R3, that's a plane or something, and let alpha from I to S be a geodesic in S. Geodesic means its acceleration is always orthogonal to the sun or point in the surface. Okay, be a geodesic in S with alpha dot not equal to 0. Then a vector field X tangent to S along alpha is parallel along alpha. That is, we want to prove that X dash equal to 0. If and only if both norm X and the angle between X and alpha dot are constant along alpha. So in two ways we want to prove. So proof. Suppose that the vector field x along alpha is parallel along alpha. Is parallel along alpha. Now we want to prove this norm value and the angle between these two are constant. Then d by dt of norm of x square is equal to d by dt of x dot x. Now this is equal to 2x dot x double. Okay, since x is along alpha is parallel along alpha, this x dash should be equal to 0. So this value is 0. So here we can note that since x dash equal to 0. Now this implies your norm of x is constant along alpha. Now given that alpha is a geodesic, so since alpha is a geodesic in S, we have alpha dot dash equal to 0, which implies your alpha dot is parallel along alpha. Now we have got x and alpha dot are parallel along alpha. Thus, vector field x and alpha dot are parallel along alpha, comma, the angle between x and alpha dot is constant along alpha. What's the reason? We have studied the properties. So property, you cannot hear the property. By property, cos inverse of cos inverse of x dot alpha dot by norm of x into norm of alpha dot is constant. Is nothing but the angle between these two, x and alpha dot. So we have proved one part. Now conversely, we want to assume that both x and the angle between x and alpha dot are constant along alpha. And we want to prove x is vector field x is parallel along alpha, that we want to prove. So conversely, suppose both norm x and angle between x and alpha dot are constant along alpha. Let T naught belongs to I and V belongs to S of alpha of T. Be a unit vector, orthogonal to alpha dot T naught. Let V be the unique parallel vector field that we have proved in the previous theorem. Let V be the unique parallel vector field along alpha such that V of T naught is equal to, then norm of V equal to 1, then norm of V equal to 1 and V dot alpha dot equal to 0 along alpha. So we can follow this. I will write in this bracket. We have norm of V is a constant. along alpha. But norm of v of t naught, nothing but by definition norm of v of t naught. Now v of t naught is nothing but norm v, and norm v is equal to 1. So what you're having is norm of v is equal to 1. Also v dot alpha dot is constant along alpha. It's constant along alpha. But when you're finding v dot alpha dot of t naught, we get it as v of t naught, right, dot alpha dot of t naught. Now this is equal to 0. This is normal plane, this tangent plane, so this is 0. So which implies v dot alpha dot equal to 0. Close bracket. That's what you got is this alpha dot of t comma v of t is an orthogonal basis is an orthogonal basis for S alpha of t for each t belongs to I. Each t belongs to I. Thus there exists smooth functions f comma g from I to R such that x equal to f alpha dot plus g into v, means linear combination. So x can be written as the linear combination of alpha dot and v. Now cos theta is equal to x dot alpha dot by norm of x into norm of alpha dot. Now this equal to, I can write x as f alpha dot plus g v. This is taking dot product with alpha dot by norm of x into norm of alpha dot. Now this equal to f into this f into alpha dot dot alpha dot. I'm writing f into alpha dot dot alpha dot plus g into v dot alpha dot, right, by norm of x into norm of alpha dot. Now this can be written as f into norm of alpha dot square, and this quantity will become 0 by norm of x into norm of alpha dot. The reason is since uh, v dot alpha dot is equal to 0. So we get this as f into norm of alpha dot square by norm of x, the norm of alpha dot. So what you assumed? So we have assumed that norm x and angle between these two are constant. Thus cos theta, we have found it as f into norm of alpha dot square. Oh, some alpha dot can be get cancelled. What we're getting is norm of alpha dot f into by norm of x. Now call this as your equation 1. And mm, and norm of x square, that's equal to x dot x, that's equal to f alpha dot plus gv quantity dot f alpha dot plus gv. Now this will simplify as equal to f square into norm of alpha dot square plus g square into norm of v square. Remaining terms will get cancelled. So this is equal to f square into norm of alpha dot square plus g square. The reason is since norm of v square equal to 1. Call this as equation 2. So since norm of v is equal to 1. So we have stated earlier. Now what into this constant we have assumed. Since theta comma norm of x and norm of alpha dot are constant along alpha, constant along alpha from 1 and 2. 1 and 2 gives f and g are constant along alpha. F and g are constant along alpha. Thus, what you're having is x equal to f alpha dot plus gv, where f and g are constant along alpha. And g are constant along alpha. Thus, x is parallel along alpha by property 4. Thus, x is parallel along alpha by property 4. So this is the proof of the corollary. Okay, hope you understood this corollary. We have proved in both ways. That is, when S is a two surface in R3, let alpha from I to S be a geodesic in S with alpha dot not equal to 0. Then the vector field X tangent to S along alpha is parallel along alpha if and only if both X and the angle between X and alpha dot are constant along alpha. So with this, I am winding up today's session. Thank you for your patient listening.